Good afternoon. I'm Spot On Weather Meteorologist Matthew Euler, and welcome to the video. Today I'm going to be discussing sea surface temperature anomalies and past winters. Specific focus will be on the overall winter temperature anomaly pattern across the United States, and I'll really be mainly focusing on the Pacific Ocean and those sea surface temperature anomalies. There's a wide range of winters that we've seen in the past across the United States as far as colder versus warmer, snowier versus not so snowy. And I really want to take a look. I did some research into sea surface temperature anomalies as well as the past winter temperature departures for the U.S. So let's take a look at the video. Starting off with the overview. The Pacific Sea Surface Temperature Anomalies, SST is the abbreviation for sea surface temperature. These greatly impact the downstream United States weather during the winter season. We have to look upstream if we live in the United States to see what's going on with those water temperature anomalies. The atmosphere-ocean interaction is extremely dynamic and has led to warmer, colder winter temperature anomalies across the United States. I've got a lot of experience out on the water as a meteorologist, and I've seen it firsthand, the amazing dynamics involved between the ocean and the overlying atmosphere. Things change in some cases change very rapidly across this interface between the ocean and the overlying atmosphere. So my goal overall is to examine the relationship between sea surface temperature anomalies, primarily focused on the Pacific, and past U.S. winter temperatures. The focus, by the way, is not inclusive only on the tropical sea surface temperature anomalies that are synonymous with El Nino and La Nina episodes. I also focused further north. My main interest here was to look north of 20 degrees north latitude in the North Pacific Ocean and kind of look at the different types of setups. We also must pay attention to sea surface temperature anomalies in the middle latitudes, and that's really why I wanted to focus not only on the tropical latitudes, the Nino 3.4 region, but look a little bit further north. I'm going to start things off again just by rehashing everyone to the Pacific Decadal Oscillation. It's abbreviated PDO. Now, this is a long-term fluctuation, typically in a 20 to 30-year cycle in the water temperatures across the Pacific Ocean, and we look primarily north of 20 degrees north latitude. Now, there are two phases associated with the PDO. There's a warm, positive phase and a cool, negative phase. The cool negative phase is typically characterized by this cool wedge of water lower than normal sea surface heights and those ocean temperatures in the eastern equatorial Pacific, and you typically get this warm horseshoe shape or pattern of higher than normal sea surface heights connecting the north, west, and southern Pacific. The warm or positive phase of the PDO is characterized by West Pacific Ocean being cool with a warming wedge to the east. This is an example of the different phases and the time periods they occurred. The cooler PDO phases occurred from 1947 to 1976, and then again from 1999 to 2002, while the warm phase of the PDO occurred from 1977 to 1999, as well as 2003 to 2006, and as well as 2014. Now, I want you to notice, again, we talk about it being a long-term fluctuation on the order of 20 to 30 years. You notice we had a cooler PDO phase predominant from the years 1947 and 1976. So that covers just about that 30-year period. And then that warm phase then just picked up where the cool phase left off from 1977 to 1999. So, we talk about El Nino and La Nina lasting on the order of 2 to 6 years. The PDO in general is a much longer lasting teleconnection. Right, so why do we care about the PDO? What's the big deal? Why am I talking about this in this video? Well, changes in the location of these warm and colder water masses across the Pacific Ocean typically alter the path of the jet stream. And those changes in the jet stream then result in considerable long-term changes in the United States weather during the winter season especially. Now the PDO can combine with El Nino and La Nina conditions to affect the temperature and precipitation patterns. For example, a warm or positive phase of the PDO can enhance an El Nino episode. So we have the warm phase of ENSO, the El Nino, in conjunction with the warm positive phase of PDO. They work both together in the same direction, known as constructive interference. This can amplify the effects of the warm pool of water along the U.S. West Coast. And stronger, more frequent El Nino phases are associated with the warm PDO. And this occurred quite frequently from the mid-1970s through the late 1990s. Meanwhile, the negative phase of the PDO is more associated with La Nina conditions, which, by the way, is forecast to be occurring this upcoming 2021-22 winter season. Now, the graphics on the left, I just wanted to acquaint you to what these horseshoe patterns look like, right? So the top left graphic there shows a negative PDO phase. And so you'll notice that the core of the above average sea surface temperatures are out over the north central Pacific. And then meanwhile, you have cooler than average sea surface temperatures into the Gulf of Alaska, down the west coast of Canada, down the west coast of the United States. And then, of course, further south, they are associated with La Nina in the upper left-hand graphic. Meanwhile, the positive phase of the PDO in the bottom left, this is a reverse situation. So now we have the core of below average sea surface temperatures across the central North Pacific, denoted by the purple shading. And then we have above normal water temperatures, the horseshoe ring, generally east of Hawaii, up the west coast of the United States into the Gulf of Alaska. And that is associated again with a positive phase of the PDO. By the way, this data is courtesy of the NASA Jet Propulsion Laboratory, as well as research conducted by the University of Washington. Looking at the cyclical nature to the PDO, okay, the red vertical bars above the zero line indicate that positive warm phases of the PDO, while the blue vertical bars dipping downward below that zero line indicate the negative or cold phase of the PDO. So taking a look at how this has changed, right, you can see many more blue bars from about the late 1940s right on through to the mid-1970s. And then you see a more dominant positive phase of the PDO by the red bars there from about 1977 on up through the late 1990s. So definitely some major changes here. Dominance between the colder negative phase and the warmer positive phase of the PDO is apparent on this graphic. Overall, sea surface temperatures, they have a major impact on atmospheric circulation patterns, and they play a large role in where storms tend to develop, where they tend to move, where various air masses move. The warm positive phase of the PDO is associated with typically what you see below average sea level pressure over the North Pacific. And then the cool negative phase is associated with above average sea level pressure over the North Pacific. So warm phase PDO, think area of low pressure in the Gulf of Alaska and in the Northeast Pacific as a predominant synoptic feature, whereas a cool negative phase, think of an upper level ridge situated in the Northeastern Pacific and in the Gulf of Alaska. Right here are the different upper air patterns, the anomalies in the overall sea level pressure. Blue shading indicating below normal sea level pressure, the orangish shading indicating above normal sea level pressure. So if you look at the general graphic on the left-hand portion of this graphic, on the left, that's associated with a positive PDO, and you'll notice over the northern Pacific, around the Aleutian Islands of Alaska, we have well above normal sea level pressure associated with high pressure. The graphic, the right-hand side of the graphic there, the maroon and orange shadings, now the pattern's reversed with a negative PDO, where I now see more higher sea level pressure, anomalously higher than normal sea level pressure. And so just wanted to show you the difference between how these pressure, the sea level pressure changes between that positive PDO on the left and the negative PDO on the right. If we look at the current sea surface temperature anomalies as of today, the 11th of October 2021, we'll notice that there is a general cooler pool of water in the Gulf of Alaska, the blue shading there, and then we have predominantly a above normal water mass extending from just off the coast of Oregon in the U.S. all the way across the central North Pacific, even past the dateline a bit. And we mentioned again, if we were to identify what's going on right now with the PDO, when we have the core of above average sea surface temperatures where it is here, that generally is indicative of that negative PDO. So we have a negative PDO taking shape right now. There's also some anomalously warm water there, generally off the coast of Mexico. And then below that we have the La Nina cooler waters there in the equatorial, eastern, and central Pacific. Here's the look at the U.S. temperature slant PDO correlations. So with a negative PDO temperature correlation, a negative PDO winter, where we have the coolest pool of water situated there in the Northeast Pacific, down the U.S. West Coast with a negative PDO, we typically see above normal temperatures for the southern U.S. up to the mid-Atlantic, those winters. We look at the right, a positive PDO, the opposite effect. So now we have the above normal water temperatures from just off the west coast of the U.S. up into the Gulf of Alaska, and we typically see much colder temperatures downstream over the southern and southeast and mid-Atlantic U.S. Okay, with a positive PDO. So what is causing this? Well, those sea surface temperature anomalies in the Pacific, Northeast Pacific, north of 20 degrees north latitude, those are associated with certain atmospheric features, jet stream configurations. Typically, we would see more of troughing off the west coast with that negative PDO and those cooler temperatures, whereas with a positive PDO and the above normal sea surface temperatures off the U.S. west coast, we typically see more of an upper level ridge, this huge dome in the atmosphere with a downstream trough into the eastern U.S. So again, these sea surface temperature anomalies do make a big difference, especially when we talk about the way the jet stream is setting up. Speaking of the jet stream, here is the configuration as of today, the 11th of October 2021. You can note a little bit of a ridge there over western Canada, and then just upstream of that we have a trough, an upper level trough, and that's a negatively tilted upper level trough extending from the northwest to the southeast. Overall in the Gulf of Alaska and the Northeast Pacific. We have a very strong jet core, jet max there in the center of the jet stream axis. That's denoted by that maroon coloring, where we have wind speeds in excess of 132 knots. I mean, it's a fairly flat-looking jet stream. We generally have a stronger jet stream associated with this temperature contrast between the cooler water in the Gulf of Alaska and that warmer water to the south. Now, the stronger the temperature difference between these two water masses, the stronger the upper level jet stream is going to become, the stronger the winds are going to blow within it. So this is just showing you, looking at sea surface temperature anomalies today, with a negative phase PDO taking shape and what the actual jet stream looks like right now as of today, the 11th of October. Now this is huge for the winter season. Why? Because we in the United States live downstream of the Pacific. So how these patterns shape up in the Pacific play a huge role in how our jet stream pattern shapes up across the United States, as well as our temperature regime, as well as how stormy or dry the conditions are. There's conditions, there's times during the winter season where the Pacific teleconnections can actually dominate everything, where you get more of a stronger west to east, almost like a fire hose effect pointed towards the west coast of the United States. And the more flat or west to east that jet stream, the stronger that jet stream, the greater the probability it's going to be mild from the west coast to the east coast of the United States. Here's the upper air pattern from the northern hemisphere. This is courtesy of Tropical Tidbits website. General blue coloring indicates where we have troughs, where we have lower 500 millibar heights, okay, lower than normal. And then the maroon shadings generally indicate above normal heights associated with ridges. So right now what we have is that ridge kind of poking up into the western Canada, the coast of Canada. We have that upstream trough from that over the Gulf of Alaska, over the eastern end of the Aleutian Islands. And then we have another much deeper trough across the western United States now, stretching from basically Oregon, Washington State, Idaho, down into Nevada. And that is producing some unseasonably chilly air out in that particular part of the United States today on the 11th of October, 2021. In fact, they're going to be seeing their first significant snowfall of the season with that anomalously strong or deep trough. And then over the United States, over the east coast of the U.S., we have an upper level ridge which extends quite far to the north, all the way up towards Baffin Bay. So again, just wanted to show you what the pattern looks like. Now I'm going to go back and look at some of the past winter seasons. We're going to take a look at, on the right, I'm primarily looking at sea surface temperature anomalies with those two graphics on the right of each slide, and then I'll have an actual the winter theme of the temperatures on the left. So I did some select winter seasons, and I thought I would just compare the water temperatures across the Pacific Ocean, those anomalies, and what actually occurred with the land temperatures over the United States for those respective winters. So the first winter I'm looking at and examining is the winter of 1981-82. And just to get you familiar with the graphic on the left, whenever you see an aqua or a blue or a greenish color, that indicates below normal temperatures. General white coloring on the graphic on the left for each slide is going to indicate near normal temperatures. And if I have above normal temperatures, that's going to have a yellow to orange to maroon shading. So just want to let you know and get you familiar with these temperature departure maps, the one on the left there for each slide. Now, the graphics on the right show those sea surface temperature anomalies. Again, yellow indicating above normal temperature anomalies in degrees Celsius, and blue shading below normal water temperatures in degrees Celsius. And let's go ahead and take a look at this winter now. So during this particular winter, 81-82, we had a neutral ENSO. We had colder than normal in the northern plains. And then we had also colder than normal conditions for the Midwest to the East Coast. So overall, El Nino neutral winter. If we look at the anomalies there in December 81 on the right, January 82 for the water temperatures, generally not too far removed from normal. There was a little bit of a cool pool of water there in the northeastern Pacific in December 81. 82-83 winter season. Now notice the changes here. Now we have the yellows and the oranges, which indicates very mild conditions for the winter, above normal temperatures actually. The green shading indicating slightly below normal temperatures. So in this particular winter, if you look at the graphics on the right for the water temperature anomalies, this was a winter dominated by a strong El Nino. You know, we're looking at 2.5 to 3.5 degrees Celsius above normal water temperatures in the equatorial, eastern, and central Pacific Ocean. Overall, it was a warmer than normal winter for the northern U.S., like I mentioned, close to normal for the mid-Atlantic. So this was a winter that was really, really dominated by that stronger El Nino. Look at 83-84 winter season. Much of the United States for the 83-84 winter season, from December to February, generally below normal. Not many places were above normal outside of southeastern California that winter. If we look at the temperature anomalies, the water temperature anomalies there on the right for November of 83 and December of 83, we'll notice a weaker El Nino signature as well as some warmer than normal temperatures there off the western United States associated more with a positive PDO. So colder winter overall for 83-84 for much of the United States, and there's your correlation of water temperatures in the Pacific on the right. Now I moved it forward a little bit now in time to 1990-91 winter season. And this was a very mild winter for the eastern United States, the East Coast up to New England, down to Florida. Near normal pretty much through the central United States, then below normal with the green shading across the western U.S. This was an El Nino, basically an ENSO neutral winter. So not an El Nino, not a La Nina, and we had a warmer than normal East Coast. If you look at some of the temperature anomalies in the North Pacific, though, look at the anomalies there in November 1990 and December 1990 of those sea surface temperatures off the coast of Japan and the Northwest Pacific. They were on the order of 1.5 to 2 degrees Celsius above normal that specific winter. We also had cooler than normal temperatures actually off the east coast of the United States. 97-98 winter season, strong El Nino yet again. If you look at the graphics on the right, we're looking at 3.5 to 4.5 degrees Celsius above normal temperatures in November and December 97 across the equatorial, eastern, and central Pacific. Look at the temperature departures for the United States from December to February 97-98 on the left. Very mild. Minnesota, Wisconsin, Illinois, Michigan, Indiana, Ohio, Pennsylvania, right up into New England. Mid-Atlantic, very mild winter. Only area of the U.S. this particular winter that was cooler than normal was Southern California, Arizona, into New Mexico. And I'm not looking at a precipitation departure anomaly chart here, but I would bet that being a strong El Nino, we had a very active storm track to the south across Southern California into Arizona and parts of New Mexico. And those increased clouds kept temperatures cooler than normal in those locations that winter. The 2001-02 winter season showing generally that we have cooler than normal water in the Gulf of Alaska on the right. Then we have more of, this appears to be more of a warmer than normal across the central North Pacific. And so by December 2001, those water temperatures were fairly cool off the U.S. West Coast and the Gulf of Alaska. And we generally had above normal conditions. We had developing La Nina. It wasn't quite there yet. But we had a very warm winter in the upper Midwest to the East Coast in the 01-02 winter season. The 02-03 winter season, things kind of switched around here. From the Midwest to the East Coast, we generally had a cooler than normal winter. And the above normal weather generally extended from the Rockies to the West Coast of the United States in the winter of 02-03. We also had a developing El Nino, and it was another fairly strong El Nino. But you'll notice this particular El Nino is a little different from the 97-98 winter season. You see how this 97-98 winter season El Nino, those water temperature anomalies, the maroon shading, go all the way to the west coast of South America? Now look at this winter. The winter of 02-03, they generally go further into the central Pacific Ocean. Also note that we had more of warmer than normal water temperatures on the order of 1 to 1.5 degrees Celsius above normal in the Gulf of Alaska this particular winter season. And we had a downstream trough predominant across the eastern United States that allowed colder air to move south from Canada and from the higher latitudes. Look at the 2010-2011 winter season. It was another cold winter season. From the northern plains through the Midwest to New England down to the southeastern U.S. It was a pretty cold winter overall in 2010-11 winter season. And you'll notice the dominance of blue shading on those graphics on the right. Sea surface temperature anomalies on the order of 1 to 1.5 degrees Celsius below normal. And in November and December 2010, look how far on those graphics on the right the blue shading extends, well out past the international date line at 180 degrees west longitude. You'll notice also that we had below normal water temperatures in the northeastern Pacific for this particular winter season. The 2014-15 winter season, this was truly a case of a nation divided. I was living out in San Diego at this point in time, and this was a case of the ridiculously resilient ridge, triple R, where we had anomalously warm water on the order of 1.5 to 2 degrees Celsius above normal from the U.S. West Coast all the way up into the Gulf of Alaska, associated with that positive PDO. It was just a crazy warm winter out in the western U.S., very little rainfall, which was terrible for the drought conditions out in Southern California, by the way. So we had an El Nino plus a strong PDO. We had colder than normal weather in the east in the 2014-15 winter season. We also had contributions from the Arctic this winter season with the polar vortex weakening. But but this is a true split winter season. Warmest out west, coldest in the east. And again, that's associated with some of those sea surface temperature anomalies over the northeastern Pacific. That definitely played a large role in how the jet stream configuration occurred, the pattern, the upper air pattern, as well as the sea level pressure changes. The 2015-16 winter season, this was a blowtorch. This was extremely warm. Look at the United States map on the left. Not many locations were actually below normal. There were none. So we had a very strong El Nino once again in the 2015-16 winter season. Look at those graphics on the right for November and December 2015. 3 to 3.5 degrees Celsius, water temperatures above normal in the equatorial eastern and central Pacific. I remember Christmas Day across southeast Virginia, this particular December 2015 Christmas. Wow, it was back-to-back 80-degree temperature days, Christmas Eve and Christmas Day. This was a case of, where did winter go? Where was winter at all this whole winter season? Again, there was a strong El Nino and also that positive PDO. If we look at the 16-17 winter season, you notice some of those sea surface temperature anomalies kind of, they migrate up more towards the Gulf of Alaska. We do have cooler temperatures moving in from the north central Pacific. Additionally, you'll notice how our El Nino quickly diminished. So we had a developing La Nina. Eventually we had warmer than normal. It was generally a warmer than normal winter for the Midwest to the East Coast, and a cooler than normal winter across the Pacific Northwest, the 2016-17 winter season. The 2020-21 winter season, one of the most recent winter seasons, you'll see, more of a La Nina was back. We had the La Nina back on the order of 1 to 1.5 degrees Celsius, below normal water temps in the Nino 3.4 region. We also had above normal water temperatures on the order of 1.5 to 2 degrees Celsius there in the north central Pacific, just south of the Gulf of Alaska. In general, the U.S. temperature anomalies are on the right. For December is upper right, and then January 2021 is the bottom right. And you'll notice it was a fairly average winter overall. So in general, things were looking really good. And then we'll move on. October, now I want to show you this graphic in particular, October 20 versus October 2021. Left is October 2020. You'll notice how much warmer the sea surface temperature anomalies were, how much warmer the water was in general in the northeastern Pacific off the west coast of the United States in October of 2020 on the left. And now this graphic on the right is this October of 2021. And notice the cooler than normal water in the Gulf of Alaska. You also notice that the La Nina conditions are a little bit weaker as of right now compared to last year at the same time. We generally have a negative Pacific North American pattern with that trough in the western United States, and the positive EPO where we have an area of low pressure that's fairly persistent in the Gulf of Alaska, and higher pressure to the south over or near the Hawaiian Islands. All right, so in general, the coolest air this October so far has been in the western U.S. into the Gulf of Alaska, as compared to last October in 2020, where the water temperatures were much warmer off the west coast of the United States. So I like to compare these sea surface temperature anomaly graphics just to get a feel for how things are looking. So overall, my final thoughts. La Nina typically correlates with a negative PDO, which favors milder temperatures across the eastern U.S. in the winter season. I wanted to start off with that main final point. So PDO and the ENSO work together. They can work together, or they can actually work in opposite directions, offset each other. But in general, if we have a La Nina winter, which we're expecting to see this upcoming winter, 2021-22, plus a negative PDO, which we typically have, by the way, right now, that generally favors milder temps across the eastern U.S. during the winter season. Now, the PDO can intensify or diminish the impacts from ENSO. If the PDO, for example, if the ENSO and the PDO are in the same phase, in other words, a warm phase or a cold phase, then ENSO impacts may become more amplified. If the ENSO and PDO, on the other hand, are opposite phases to each other, An example of this would be a La Nina year, and generally a positive PDO. If they're opposite to each other, then the ENSO impacts may be more limited. And then if we get a negative PDO plus a La Nina, then we would expect to see above normal temperatures and below average precip during the wintertime over the eastern U.S., which would indicate, again, generally that combination of a negative PDO plus a La Nina would indicate a warmer winter in general that would be ahead of us. The current PDO values, by the way, are sitting at negative 1.94, so we definitely have that negative PDO. So overall, I wanted just to take the water temperature anomalies across the Pacific, not only the El Nino, La Nina, but further north, north of 20 degrees north latitude, and just take a look at past winters in today's video. Generally, the temperature correlations to what was going on with the land temperatures of the United States versus the water temperature anomalies during specific select winter seasons of the past. This does take a lot of research. It takes a lot of time and effort. But if we can identify specific trends or patterns, then of course that will improve seasonal forecasting, especially when it comes to the winter seasonal forecasting aspect. So that's why I'm very interested in looking at these past winters, the sea surface temperature anomalies in the Pacific, as well as the temperature departures in the wintertime over the United States. So I certainly hope you enjoyed this video. By the way, these are my references from the video. I take graphics from NOAA. North Carolina Climate Office is a great resource. The NASA Jet Propulsion Laboratory, University of Washington also. I provided some material for this particular video. Again, I find this stuff very fascinating. I'll continue on with my weekly teleconnection discussions. So I'm looking at doing the next teleconnections discussion where we kind of tie and package everything together, all the teleconnections, not just the Pacific side, but also the Atlantic side, the Arctic, and the polar vortex as well. So I look forward to continuing to do those weekly teleconnections discussions. I appreciate everybody out there for subscribing to our channel. Thank you so much for supporting Spot On Weather. We provide all of this information, whether it's weather forecasts, whether it's some of these educational videos. We do this absolutely free. We absolutely love providing this type of weather input and research to all of you out there. All right. I wish everybody a great day. Hope your week is getting off to a great start this Monday, October the 11th, 2021. Hope you are having a healthy time right now. Stay safe, stay healthy, and that wraps things up. Until next time, take care and God bless everyone.